chemistry PhD degree at the Technische Hochschule in Braunschweig. At the time he was at Shell Amsterdam, he was also extraordinary professor at the University of Leiden from 1963 to 73 and special professor at the same university from 1974 to 83. In 1982, or early 1983, he came to Northwestern University and is now the Thaddeus Professor of Chemistry and Director of the Catalysis Center at Northwestern University. He is with us, at least partially, through his receipt of the Robert Burwell Lectureship for 1985. And one of the responsibilities of that lectureship is to talk at each of the sections of the Catalysis Society. And we certainly want to welcome him here in that position. So, Professor Sachtler.
Thank you very much, Bruce, for this nice introduction. And it is certainly a pleasure for me to be again in Houston, where I've been serving and where I have had so many discussions on catalysis, and also where I've found so many friends. As you said, I have now been giving lectures at various meetings of catalysis clubs in this country. Usually I was giving lectures on rather general subjects, which include work which I did in Europe before I came here, and some work which I have done here. The lecture today is of a different nature. This is for the first time that I try to present results which were entirely obtained at Northwestern University. In a field which I find fascinating, in a field which I know, however, some of you may have more experience than I have, so I'm quite interested to hear your comments and ideas about the results. The subject is, or the object of this research is the platinum zeolite system, and the zeolite in this case is always the zeolite Y. The reason for doing this research stems from two sources. We all know that solid acid catalysts have always played a large role in applied catalysis, and in the old days, these very old days, these were natural clays, later synthetic silica aluminas, and all this has been replaced now by the crystalline zeolites in their acidic form, which are obviously superior. But as soon as we come to combinations of metals with an acidic function, then we find that even now most platform catalysts, for instance, are combinations which contain platinum or platinum with amorphous acid, aluminum, for instance, whereas there is rather some hesitation to introduce platinum zeolite systems. And this shows that there is some difficulty, and there are things which are not quite understood. And that is one reason to do research about these systems. Another one is that there were claims in the literature that platinum in a zeolite behaves differently as a catalyst from platinum, say, or silica or alumina. And that was attributed to electron transfers. People talked about electron-deficient platinum in a zeolite, which behaved like a different element. Well, this idea almost struck a raw nerve, because that reminds us of discussions which animated the whole catalysis in the 1950s, when for all kinds of supports, people claimed that electron transition between the metal and the support was decisive for the activity and the selectivity of the catalyst, and that was usually presented under the general term of the electronic factor in catalysis. And as we all know, this idea has been very thoroughly disproven. There are many experiments, and from a fundamental physical point of view, it is quite obvious what happens if you have a metal in contact with a semiconducting support. Then if the two Fermi levels are different, you will of course get some electron transition. You create the contact potential or volta potential, which is given by the difference in Fermi levels, and that gives rise to a double layer, but that is safely located at the metal support interface and has absolutely no effect on the catalytic properties of the metal and the metal vacuum interface. After the books had been closed on this misconception, 10 years ago roughly, a similar idea appeared in the literature under a different name. It was then called SMSI, strong metal support interaction, and there the idea was that microscopic metal particles would be modified by interaction with the support, and people again speculated on the concept that this might be due to some electron transfer from the metal to the support. Again, much research has been done, and I think now everybody agrees. What really happens is that the support is reduced in part, and some of the ions of the support cover the surface of the metal. Okay, thank you. And the ions on the surface of the metal then can either block sites, as we have shown in the ACS meeting for the hyperformulation selectivity, which goes up by orders of magnitude, or they can interact with, for instance, the oxygen of a carbon monoxide molecule, as I have shown in Berlin last year, and in this way greatly influence the catalytic activity and the selectivity, but again, no electron interaction. So the question whether an electron transition is important in zeolites received some skepticism, but we must be fair and admit that the thermodynamics of reducing a metal on a zeolite is different from the conventional way as we do it with silica or other amorphous support, where we impregnate and calcine and get some oxide or hydroxide, which is then reduced, and the formation of water is an important parameter contributing to the energy and the entropy of this reduction process. If we have a zeolite where the metal, for instance platinum, is introduced by ion exchange, we first have a calcination process, because these ions are typically coordinated with ammonium ligands, which protect the ion, and that has first to be destroyed. Then, the literature says, there is a reduction process where you create individual zero-valent platinum atoms, which then migrate through the zeolite and may coalesce and form small platinum particles with still a high dispersion. So while here the formation of water is the driving force, we have here different thermodynamics, and while here the agglomeration takes already place in the state of the precursor, we have here in this model agglomeration only at the last state after reduction. And the idea is possible that the reduction is more difficult in this case than in that one, because the thermodynamics are less favorable, and by consequence one can imagine that some platinum ions remain unreduced, and if in small particles you have, for instance, one platinum ion and 10 platinum atoms, then that particle will of course have a positive charge, and there's nothing against it to call such a particle electron deficient. The question remains, however, whether that is of any effect to the catalysis. The the idea that just adding a charge to a metal changes its catalytic activity is not so self-explanatory. After all, if that were the case, we could simply use the anode of our car batteries in changing our catalysts. And those of you who have ever worked with a field electron microscope where you have enormous charges and enormous field strength will remember that at least for non-polar bonds, this charge has very little effect on the heat of absorption. So we felt we should investigate that. And what I'd like to do today is first briefly say something about the characterization of these catalysts, and then about their catalysis for a hydrocarbon conversion reaction. As far as the catalyst is concerned, we found DPR results very instructive. And if you first calcine the catalyst at various temperatures, the platinum-sodium Y system in this case, then the ultimate dispersion depends in a very typical manner on the temperature of the original calcination, and others have found that before. A temperature around 300 C is favorable. Below that, you do not sufficiently destroy this tetramine jacket, which protects the platinum ion against reduction. If the temperature is too high, other phenomena occur. The platinum ions may creep in the sodalite or in the hexagonal prism cages, or particles may be formed at the zeolite surface with a very low dispersion. So we further worked at this temperature, which was optimum of 300 C. And if you take such catalysts and reduce them in a temperature-programmed way, then it is useful to compare the reduction of the zeolites with the one that gets for amorphous supports. Here we have platinum on silica, and you see the reduction sets in at very low temperature, below room temperature, -15 roughly, and there is another peak above zero at roughly 30 degrees. How does the zeolite-supported platinum behave? Well, there is almost the same story. I'm now talking about the first two curves here. Again, there is a peak below room temperature, below zero at -15 degrees typically, and another one at +30 roughly. So we can reduce these platinum on sodium Y systems at a very low temperature once they have been calcined at 300 C. I will come back to that last curve in a different context in a few minutes. The surprising results are, however, emerging as soon as we compare the sodium form of the zeolite with the acidic form of the zeolite. So if you use the same program, the same pre-calcination on an HY form of this zeolite, then the reduction sets in at temperatures in the vicinity of 200, and you have actually two peaks, one at almost 250 before you can reduce this. Again, dependent on the loading, and I will come back to the curves of the reoxidation and the second reduction again in a minute. Let me first just note the differences. So first, the reduction temperature is much higher for the zeolite, the H form of the zeolite than for the sodium form of the zeolite. Secondly, if we count the hydrogen consumption, so simply integrate these curves, then we discover that for the sodium form we had typically something like 2 hydrogen atoms per platinum if we make both the corrections. So the platinum, which was actually admitted originally as a divalent ion, has survived all the calcination without getting oxidized. But on the acidic form of the zeolite, this HY for instance, we have an average valence state about 3, and that is a different experiment again, 3.3. So a significant portion of the platinum must have been oxidized to the tetravalent state, as is known to occur also on alumina.
And the third surprise is if you take these zeolites after a reduction and you have obtained the high dispersion and you re-oxidize them and then you reduce them again, then you always come back to the pattern which completely disregards these differences between the HY, sodium Y, the reoxidation. After reoxidation, the second reduction has again these typical peaks, one below 0 and one above 0, just in the same way as we saw in the previous slides for the sodium form of the zeolite. So that difference, that enormous difference in the reduction peak between the H form and the sodium form is only present for the first reduction once we have brought the ion in by ion exchange. Now, how do we rationalize that? Well, if we all agree that the highly dispersed platinum consists in very small particles in the supercage, we usually think of particles in the order of 13 atoms. That's a very convenient model. You have one platinum atom surrounded by 12 closest neighbors. That gives an almost spherical, shaped particle. It's actually an icosahedron. But you can take another model that is not essential. So we have, after the completion of the reduction, these small particles in the supercages. And then the only assumption which we make now is that when we oxidize such a particle, we will make a small platinum oxide particle in the same supercage. So the assumption I'm making is that after emitting oxygen, the platinum ions don't explode and don't go to different positions, but essentially remain within the same supercage. So where you had, for instance, a platinum particle of 13 atoms, you would have, after oxidation, a platinum oxide particle of 13 atoms. That's my only assumption. If we accept that assumption, then we must conclude that these spectra of the reduction of the reoxidized specimen correspond to the reduction of small platinum oxide particles. And there is a lot of evidence for that. If we use literature data on platinum, on coal, or on Adams catalysts, where we have the small platinum oxide particles, and if we reduce them, then we get peaks in this vicinity. Well, that conclusion immediately leads to the next conclusion. The similarity of these peaks of the reoxidized samples with the platinum in the sodium Y then forces us to assume that in the sodium Y catalyst, the platinum already formed small oxide particles during the calcination. Small oxide particles, however, with still divalent platinum. We saw that we consume two hydrogen atoms per platinum. So the chemistry which emerges from that of the process of calcination and reduction is that during the calcination we have not only the destruction of this jacket, but there is a second process. We form, of course, lots of water during the reduction, the destruction in oxygen, and this water reacts with the platinum in this way and forms these platinum oxide particles, which are already the agglomeration particles, plus, of course, proton for charge conservation reasons. And during the reduction, we just reduce these platinum oxide particles. If that is correct, that we understand that after reoxidation or reduction, we just remain in this loop here. And nothing else has to happen. We just have to enter the loop in the beginning by the first calcination process. Well, there are some independent evidence in favor of that. I promised you to discuss this third curve on this slide, which was a curve where we had platinum with a second material, in this case iron, on the stabilizes the high dispersion of the platinum, but we see now here that this spectrum is shifted to higher temperature compared to the TBR spectrum without the iron. So it appears that this iron is already interacting with the precursor. So if we assume that we have here some small platinum oxide particles, we must conclude that here the iron makes part of these oxide particles. So we have, so to speak, a mixed oxide of a few platinum atoms and one or two iron atoms in it, and then we reduce, the iron is only reduced from the trivalent to the divalent state, and the platinum is reduced, but we need a somewhat higher temperature, of course, to reduce the mixed oxide particle than the single particle. Now, how does that then explain the large difference between the H form and the sodium form? Well, we have just to consider that this important equation is an equilibrium equation. So in the case of the sodium form, of course, the equilibrium goes from the left to the right. But in the case of the H form of the zeolite, the equilibrium is unfavorable because we have this high concentration of protons. So that reaction does not take place. So here the platinum ion, after being diluted, after being deprived of this tetramin jacket, cannot react with the water. It will then react with the oxygen and forms the tetravalent platinum oxide, and that explains the results of the integrated reduction of the PPR of the acidic form, where we then needed the hydrogen consumption of 4 hydrogen atoms per platinum. But once you have achieved the oxide and the metal particle, then you are in the same loop for the HY as for the sodium I. That difference is only developed in the precursor state. This gives us now the model of the catalyst. So we have our sodium Y or our HY form with these supercages, which you all know. And in the supercage, we assume these platinum particles. Again, if this model of the 13 atoms is correct, it's a very convenient model, then you can understand that is a particle which stays inside the supercage, but it is just too big to go through the windows, so therefore it has to stay inside and has a rather high stability. Now, how does this system behave as a catalyst? The test reaction which we have chosen is the conversion of methyl cyclopentane with hydrogen at a fixed temperature and at a fixed pressure. That reaction provides us with a lot of interesting information. The methyl cyclopentane molecule can first ring open and form a paraffin molecule, and it can do so in 3 ways. You can get normal hexane, 2-methylpentane or 3-methylpentane, depending which of the 3 of the 5 bonds inside the ring you cut through. Secondly, it can get ring enlargement, and then you get C6 rings and you get a benzene. Thirdly, you can get hydrogenolysis and cracking products with less than 6 carbon atoms. And finally, you get alkylation, so products with more than 6 carbon atoms. And this you can study now for the monofunctional platinum on sodium Y, for the bifunctional catalyst with the acidic form of the zeolite, and you can compare that with the physical mixtures of the 2 pure complements. And the motivation of the objective, I have already explained. We want to see, is it true, is there a difference between the platinum and the zeolites in this form and that form, compared to what we know of platinum without support or on the classical amorphous support. And of course, we have to study the mechanism of the ring enlargement, and we have to study the mechanism of the ring opening, and that's quite fascinating. And we have to see for the bifunctional catalyst how the carbenium ions are formed, and I won't talk today about much at least about the deactivation. All that work about the catalytic reaction is actually part of the thesis by Ming Child, whereas the work I mentioned first about the characterization of the catalyst by means of the TPR method that was done by Dr. Park and by Dr. Zhao in our group, the Atlantic Northwestern University. Well, let's jump to the results. The first interesting comparison to know our reference is with the platinum on the silica, and we have here compared three different dispersion, lower, mid, medium, and a high dispersion, as you see on the platinum on the silica. And these are under our standardized conditions the products, and what you see is that the name of the game is ring opening. For the neutral silica, in the absence of an acidic function, the ring opening prevails. There is a little bit of cracking, and that is then the metal cracking to methane, and there is a slight trace of a demethylation and of a C6 formation. But the distribution of the three products, normal hexane, 2-methylpentane, and 3-methylpentane, depends on the particle size. Well, that, of course, is not new. François Go in Strasbourg had studied that very extensively, and we can just compare our results of the silica with his. If you plot the ratio of the 3-methylpentane divided by the normal hexane against the dispersion, then for those alumina supported and our silica supported catalyst, you get a universal curve which shows that the ring opening depends on the particle size. That is not the new thing. Now, the first comparison with the zeolite is shown in this slide and in this transparency, I should better say. And you see that there is, in first sight, the same general picture. The platinum on the sodium form of the zeolite behaves just as the platinum on silica. The ring opening is the main activity. There is some difference in the products, the distribution of these three ring opening products, and I will discuss that point at the end of the lecture, and at this moment just say that the reason for that is basically a geometric reason. But there is no point, no argument at this stage to postulate any electronic interaction which makes platinum and the zeolite different from the platinum on the silicon. Now, how is it with the platinum on the acidic form of the zeolite? If we take HY, and we have studied two, one with a low acidity and one with a high acidity. Without platinum, the low acidic form doesn't do anything at this temperature. The high acidic one is a typical acidic catalyst you recognize now. Cracking is mainly the formation of isobutene, isopentane. All what we have learned about the carbenium ion reactions we find confirmed here, and some ring enlargement to cyclohexane. If we combine the platinum with these acidic forms, then we first notice that even the low acidic form, which without platinum had no catalytic effect, changes the pattern of the platinum. There is still ring opening, but much less than in the sodium case, and there is now a considerable amount of ring enlargement. And if we take the stronger acidic form here, then the ring opening is very, very low. It's now really only a trace, and 70% of all our reaction product is the ring enlargement to the C6 system, which then, of course, with the platinum gives a distribution bit of benzene to cyclohexane near the equilibrium value. And there is a considerable amount of alkylation, also molecules with more than the 6 atoms, carbon atoms. Now, the question which we have to study is how does that behavior compare with the behavior of platinum in combination with an acidic function, but not on an acidic carrier. And in order to make that comparison easy and not always bore you with all these detailed numbers, I have lumped together the numbers of the previous slide. So this is platinum silica HY and platinum HY, and we see we lumped them four main reaction types, you find what we saw in the previous slide again, 70% ring enlargement for the platinum HY. Now, how can we find out whether the platinum in this form has acquired somewhat different catalytic behavior or properties as compared to platinum and some other support? Well, the answer is very obvious. Now we must compare physical mixtures or even layered beds, and this is what we did. Here we have typical examples. This is again the color which you saw before. Here we have platinum on an inner support physically mixed with HI, and here we have even a sandwich bed where the platinum function is at the beginning and the end, and the acidic function sandwiched in between. The direction of the flow in our flow reactor is given by the arrow. Now you can use your own imagination to interpret this. My first impression when comparing this with that is the similarity, which is so striking that also in the physical mixture the ring enlargement is now the main thing, while you remember the platinum silica alone without the acid had mainly given us a ring opening. And we do that, we find that at a conversion which is still low enough that we can dismiss any trivial explanations that, for instance, there are no molecules left to give any ring opening. So the similarity is very striking. There are, of course, some differences, but we must not forget a physical mixture is not the same thing as a co-impregnated catalyst. If molecules in a bifunctional catalyst have to shuttle between one side and the next side, and of course it makes a difference whether you find both sides in the same cavity or the same pore, or if the molecule has to creep out of the pore of one support and creep into the pore of the other support. So this so-called intimacy requirement is sufficiently to explain this slight difference that the ring opening is retained a little bit better for the physical mixture than for the co-impregnated or catalyst. The deactivation depends very much on the type of catalyst. If we use the platinum sodium form, the one which gave the ring opening, as you remember, then the deactivation is low and quite comparable to the platinum on silica. But if we have the platinum in the HY form, then results look very interesting. First, you see that the acidic form only, that's the red curve, deactivates much faster than the catalyst with the platinum. Well, I think that is not new to anybody who is familiar with hydrocarbon conversions. The acidic function is killed quite fastly by carbonaceous residues, polymers of these carbenium ions, in particular the thiophenol carbenium ions, which polymerize and give the usual coke. The reason why platinum was originally introduced, if I were informed, into these catalysts is just to keep the catalyst clean, and as Cabrera has shown, the mechanism is hydrogen spillover, hydrogen dissociating with the platinum. So we find that confirmed, but that is not exciting. Platinum protects the acidic function against salt poisoning. The other interesting thing is, however, that the acidic function initially, before this poisoning sets in, has a high activity, which is comparable to that of the bifunctional catalyst. But that is not the point at the initial activity. It starts from a very low one, goes through this maximum until it then falls into the self-poisoning trap. So there must be a mechanism how the acid function, even in the absence of the platinum, can do its job, a job which is basically a job of having the carbenium ion chemistry running faster. Well, that brings us to the mechanism of these carbenium ions. We all know that for ring enlargement, which is the main function, the decisive process is that you somehow must make a carbenium ion of the original molecule by Well, if we look at the chemistry of liquid superacids, then the name of the game is just hydride ion transfer. Once you have some carbene ions from somewhere and you have a steady state population, you just have this hydride ion transfer so that the new molecule donates this H- ion and it becomes a carbenium ion, which then isomerizes and the reaction product in the carbenium ion world is returning to the upper world by the same process, by then taking over the carbenium ion. That's how it works in the liquid superacids. On the bifunctional catalyst, we usually assume another mechanism is operative, where we have these metal sites which first transform the molecule to the olefin, and the olefin reacts with the protons, and then we have the same conversion, and into the steady state requires, of course, that the molecule is again redonating the same proton which it has first borrowed from the surface, and you get the olefin, which is then disproportionating, in this case, to benzene and cyclohexane. So this is the bifunctional catalyst, as we have all learned from Mills and others in the literature. This is the direct ion transfer, and the actual message is both processes take place in the absence of platinum. It takes some time before you build up your carbene ion concentration, but then you can, as we saw, reach virtually the same activity as in the presence of platinum. The main reason why the platinum is there is to keep the catalyst clean, and once it is there, then of course the bifunctional mechanism is welcome. Now we still haven't answered the question, why is the addition of the acid not only adding something new, the ring enlargement, but also reducing the original function of the platinum in ring opening. And therefore these layer beds are of some help. If you remember, for the ring opening, the physical mixture had a very low activity, the same as the platinum on the HY. And if we now dissolve this, rather than having a physical mixture, we take either a layer bed with the platinum function upstream or the platinum function downstream, or the sandwich bed, then we notice that this ring opening is only reduced if the platinum function is downstream. And then it is reduced to this value. So one explanation for the low ring opening activity of the combined system seems to be that the acidic function creates some poison which poisons the platinum function for the ring opening. That is one explanation. It is not the only one. After all, you still have a value which is significantly higher than that one here. So there is another possible explanation, and I think both contribute. We have not discussed here the mechanism of ring opening, because that was again studied extensively by François Gau. The ring opening reaction requires, according to Gau, rather unsaturated intermediates, like this dicarbene. He even postulates dicarbines, although that is under discussion. And the carbenium ion reactions we have seen in the case of the platinum catalyst that makes use of the olefin. So if we have somewhere a unsaturated intermediate which can go either way, either to the carbenium ion or to the ring opening reaction, then it is easy to understand that a high efficiency to direct the intermediate, the unsaturated intermediate into the carbenium ion frame will drain it from the ring opening frame. So here we have a second possible reason why this ring opening reaction is reduced in the case of the bifunctional catalyst. The remaining ring opening that may actually be due to the acidic function. We have therefore also studied this very, very slow ring opening activity of the acidic function, and I won't go into details. There was some quarrel in the literature whether the ring opening the acidic function will give the branched product or, as some authors found, the linear product. The answer, we think, is rather simple. It depends on the conditions. If the primary product is, of course, for the carbenium ion, the tertiary carbenium ion, after ring opening you get the secondary carbenium ion, and if you leave that alone to isomerize, you will get branched products. If you have a very efficient hydride ion transfer process, so in other words, if you have a high partial pressure of your paraffin, then you will immediately freeze in the primary product, which is here the linear shape. So up to this point, remembering the reason why we did all the work, we can have some first conclusions. The catalytic performance of this highly dispersed platinum is virtually equal for zeolite supported platinum and platinum supported amorphous silica. So we find very little support for any mysterious methodological effects of electron transfer transmutating platinum to other elements, as has sometimes been postulated. We secondly have found that the ring enlargement is, of course, catalyzed by the acidic sites, caused by carbenium ions, and the rate is significantly increased by the incorporation of platinum because you have this bifunctional route, and as we saw, we protect the catalyst against poisoning. We finally have the study with the ring opening, and I needn't read that. As I said already, there is rapid poisoning, so while the platinum protects the acidic function against poisoning, the acidic function just is a very ungrateful customer and poisons the platinum function with the junk made on the acids. But there is also some reason to assume that a common precursor is responsible, and that this is another reason contributing to this suppression of ring opening as soon as the acidic function is present. And I briefly showed that the acid catalyzed ring opening can lead either to branched or unbranched molecules, depending on how quickly you freeze the primary carbenium ion by hydrogen ion transfer. So far, I have emphasized the similarity, the absence of differences of platinum on silica and tubular mixtures and platinum in the zeolite. But if you still remember the first part, there was one difference, and that one difference I have now to discuss before I can finish the lecture. And the difference concerns the selectivity of the ring opening. What is the relative abundance of these three ring opening products? On the amorphous support, we have seen it is dependent on the particle size, on the hydrogen dispersion, and if we have a very high dispersion, we get the statistical distribution, and since we have two bonds to be opened giving normal hexane, two bonds to give the 2-methylpentane, and one bond which will give the 3-methylpentane, we find on these high dispersed catalysts, high dispersed platinum on silica and on alumina, this ratio of 2 to 1 for these products. And that was the curve which I had shown in the beginning of this lecture, where the advantage is here we have no assumptions. We just plot two measured quantities against each other. We plot the ratio of the 3-methylpentane over the normal hexane versus the HPT ratio. But if we use that universal curve and now see what happens with our zeolite, then this is significantly higher. So with that quotient where the normal hexane is in the denominator, we must say that the zeolite we make less normal hexane than we would with the same dispersion do on a amorphous supporter. And the difference is a factor 2. Since that distribution is nearly thermodynamic, you have first, of course, to verify that there is no secondary reaction, and the answer is yes, there is these trivial explanations. So we have to find an explanation. What could be the reason why on the zeolite you make the platinum in the zeolite, in these cavities of the supercages, have this selectivity that less normal hexane is produced as compared to the two others and as compared to the same particle size. We should, for tackling that question, remember that the cyclopentane molecule is actually a molecule which divides the hydrogen atoms, apart from those in the methyl group, in two groups. One on the, as I've shown it here, below the ring, and the others, which I have here shown by small letters H, above the ring. We know that from the deuterium exchange experiments. You are familiar with that. At low temperature, you can easily exchange one group, but not the other group. You need a higher activation energy if the ring goes changes over from one position to the other. So the usual mechanism of the exchange reaction, as you know, is that you have this alpha-beta migration. So the ring, once absorbed with one phase of the surface, it will make several of these rounds, and each time the CH bond is broken, it can be reformed by the other isotope. And so you easily exchange the hydrogen atoms at one side of the ring. If you want to come to the other side of the ring, then you have to roll over the molecule, and that is shown here in this drawing on scale. And so the molecule which was first lying on its back is now in the other situation lying on its stomach, so to say, and has to go through this intermediate, which has a somewhat higher activation energy. Well, these deuterium exchange experiments are usually done at a rather low temperature, so even that activation energy to roll over is small compared to the activation energy for ring opening. So we can assume fairly that under the reaction conditions where we study the ring opening, that process will also be fast in a normal catalyst, and the molecule will roll over. And I have now marked one of these hydrogen atoms because that is the important one. If you want to rupture the CC bond between the tertiary carbon atom and one of its two neighbors, so you have to form two metal carbon bonds in alpha-beta position. So you have to dissociate that hydrogen molecule, hydrogen atom, on the tertiary carbon atom. And that can evidently only be done in this position, because that is the only carbon atom which has a hydrogen atom only at one side of the ring and not at the other. So if it were impossible to roll over, then this this position would be favorable for cutting this bond, forming metal-metal bonds, and so then this CC bond could be ruptured with the same chance as any other CC bond in the ring. But in that position, that would be impossible, because here the hydrogen is pointing to the wrong side, away from the platinum surface, and so that tertiary carbon cannot form a metal carbon bond. Now, as long as it is easy to roll over from one position to the other, there is no problem. So for platinum on any amorphous zeolite, it doesn't matter so much what position the molecule has when it first is chemisorphed on the surface. The rollover process is easy. So during one residence, we can say every carbon atom has an equal chance to form a metal carbon bond, and if this neighbor does the same, then you will have the CC bond rupture. However, in order to roll over, you must have some clearance, some headspace. So the rolling over situation is a situation where that distance between the platinum atom and the hydrogen atom on the top is 5.33 angstrom. And that is not a problem, of course, for a platinum we have reasons to assume that one of the models for the high dispersed platinum is this 13-atom particle, which is just nicely fitting in it and too big to go through the cages, through the windows, but small enough to do catalysis. Well, for such a particle in a supercage with the 3 windows, it is not difficult for a metal cyclopentane molecule can be solved on the surface of the platinum particle, but it will be impossible, of course, to do the rollover mechanism, because now you need these 5.3 angstrom, whereas here the particle fills half the volume roughly, and if these numbers of our model are something like a good approximation to the reality, then you have a 30 minus 8.3, that would be 4.7 angstrom, which is certainly not sufficient for the particle, for the molecule to roll over. We therefore feel that this difficulty of geometrical restriction in these supercages for the molecule which is absorbed to roll over reduces its chance to come to the other side than the one where it happens to be absorbed in first instance. And since there is a 50-50 chance, of course, that it is absorbed in either of that situation, only 50% of the cases, namely these one, will lead to the ring opening, including the tertiary carbon atoms, so including the normal hexane, whereas in the other 50% of the cases, now only the 2-metal and the 3-metal pentane can be formed. So the decrease of the hexane formation, relatively speaking, by a factor of 2 can be understood with this simple model, we believe. This shows that the only difference which we have been able to find between platinum on these zeolites, even the acidic forms, and platinum on the amorphous supports, has basically a geometric origin which is easy to understand, and one can speculate about further refinements, which I won't do here now, but there is no principal intrinsic difference in the catalytic activity of the platinum in these zeolites as compared to platinum with other supports, at least for the reactions which we have studied here, which of course do not include any polar bonds, we should be clear about that. We have to conclude there is not much space for any methodological differences, not much room for speculations in this about these electron transfer effects of the support changing the catalytic property of the platinum. I have in this lecture talked to you about a solid catalyst and a gaseous molecule, or 2 molecules, hydrogen and metal cyclopentane, which was reacting. Maybe that at the end I should say a few words, if I may now have the slides, about a solid liquid interface. Have I to do something here, or do you do that? That is the place where I now earn my bread. This is here Lake Michigan. At your left, you see in the distance, looking southward, the loop of Chicago, and you see at the foreground one of the 2 campi of Northwestern University. And if we proceed a little bit further, then we see that artificial land fill. The university was there before the city was starting to grow around it, so that the university wanted to expand several years ago. They had to fill in part of the lake, and this created this artificial lagoon. And if we see the winter season, then we find the scenery which I understand you in Houston dislike totally, and we are sometimes quite happy with this situation. And the fine thing about winter is that after every winter you will have some spring, and then you can have here in the campus some parks where you really wonder, are you in Illinois or in the Netherlands? This is an architect's drawing of an attachment to the Technological Institute, which was made 2 years ago for a new center devoted to research on catalysis. Since Ipatjev and Clementines and Bergall, it had been a dream of people in Northwestern, of course, to have a real lab concentrating on catalysis and surface science, since altogether 15 faculty members do work in this area or closely related to this area. This is now taken a few weeks ago, and that is not the architect's drawing, but that is now a real photograph of the new catalysis center. You see it is being built and it's almost ready, and we hope that by the end of this year we will be able to move over it. There is now this connection being built between this new catalysis center and the building at your right hand here, which is the Technological Institute, where the chemistry department, the chemical engineering department, and the material science department, the three which have this strong cooperative effort at heterogeneous catalysis are located. So if you visit us next year, then I hope you will be able to see us busy in this new catalysis center. I thank you very much for your attention.